All right, so bear with me. Our notes for this first day in our quadratic functions packet it's a rather lengthy day, but they're fairly straightforward. A lot of it is learning what different things on a quadratic function are called. So this is the base for quite a bit of information we are going to be discussing during this module. It's a must that you understand these basic vocabulary terms. Throughout today's lesson, I'm going to give a couple of code words, and at the end, I will give you a final code word and some directions on what to do with those. So just pay attention for those along the way. The first thing in our notes, a function that can be represented by the form of f of x equals ax squared plus bx plus c is called a quadratic function. This is a new function that we are looking at. This is the first time you will have seen it. A quadratic function produces a U-shaped graph called a parabola. Please don't call it a parabola. It looks like this right here. So we're going to look at some of the key features of this graph. Specifically, this right here, this is called a parent function, which is the first thing we're going to answer right down here. Quadratic function represented by f of x equals x squared. So just simply x squared. It's called the quadratic parent function. We have to name it as quadratic parent function because we also have linear parent functions and exponential parent functions that we could also reference in math. There are various other graphs that can also get referenced. So this is specifically a quadratic parent function. This is a picture of a quadratic parent function. If you look right here, this sits right at the origin and both sides look as if they are mirroring each other, meaning I could fold along my y-axis right here and both sides would land on top of each other. So what they're wanting us to do here is to name all of the coordinates on this graph. Personally, I suggest starting right here at the origin, which is going to be 0, 0. Okay, from here, you could either choose to answer these or these. Either way, it works just fine. You are just going to name what the point is. If x is this value, what is y? So I'm just going to move to the right first, and then I'm going to go look at how the left side partners. So first I'm looking at when x is 1, which would be right here. So when x is 1, y is 1. At this point, this right here looks as if it could be a linear function just based on these 2 points. When we get to an x value of 2 and see that the y value jumps all the way up here at 4, this is where it's now different than a linear function based on what we have filled in so far. And finally, if we go over 3, it jumps even further up and it's going to be 9. Okay, so these are all of the positive x values that they've asked us to look at. Now, we mentioned at the beginning that this is showing a mirrored image. So what that means is I should see these points happening again up here. For example, this should mirror to right here. This guy should mirror to here. And this guy should mirror to here. Which means if I start at -3, I'm going to go up 9, just as if I did when I was going +3, up 9. Then next, -2, up 4, just like I went right to up 4. And finally, -1, up 1. So if you look, we have points on either side that mirror each other, which supports what we are seeing on this graph. The next thing we're going to do is we're going to label a couple of the key features using this picture. The first thing it wants is the vertex. Now the vertex is going to be either the lowest or the highest depending on the direction of our graph point. It's also considered the turning point. So our vertex in this graph is going to be at 0, 0. The next thing we're looking at is the zeros of a graph, which specifically this is going to be the x-intercepts, which is a vocabulary term you need to know, x-intercepts. Another way you can refer to an x-intercept is a 0, and this is very commonly used in quadratic functions, so it is expected that you know that those two words can be interchanged. The zeros are going to be where it crosses the x-axis, which is going to be this right here. On this specific graph, the only place it touches the x-axis is at 0, 0. The next thing we're going to look at is the domain, which is going to be moving left to right. What kind of values can this graph have? Because they are both extending upward, outward, that outward movement is what's going to help me left to right. There is no restriction on how wide this can get eventually. So my domain is going to be either negative infinity to infinity or all real numbers. Okay. The next thing we're looking at is if there's a minimum or a maximum. Again, this has to do with my turning point or my vertex. Because that vertex is the lowest point on this graph, I'm going to call this a minimum. The next thing I'm going to look at is an axis of symmetry, and this is that line that causes the graph to look like it is mirrored. I'm going to depict that line with this vertical dashed line. For quadratic functions, it will always be vertical, but it can shift depending on where your graph is located. At this particular moment, this is considered the line x equals 0, or you could call it the y-axis. For what we are doing in algebra, you need to stick with the x equals 0 because in other places you're going to have x equals whatever is happening there. But just to connect what that specific place is, it is considered the y-axis. The next thing is going to be the range, and the range is going to be how this graph is moving up and down. Now, the range is going to play part with your graph either having a minimum or a maximum. Because this is the minimum, it means it's the lowest point. No y values, so no negative y values, so these guys here, you won't see any negative values because this is stopping and turning around at 0. So my y values are going to be 0 and above. So the way I'm going to name that is that y is greater than or equal to 0. This means it could be 0 and it's any value above, meaning all of the negative values are excluded based on how this graph is turning at the vertex. All right, after page 1, I'm going to give you your code word number 1, and that is going to be the word flower. Please write this down in your notes. You're going to want it for later on. All right, moving on to our next page of notes. We are going to look at a couple of quadratic functions and identify the key features based on the information that they want us to look at. In this first equation, we are looking at f of x equals x minus 1. What I want us to do is I want us to look at this as if we don't know what it is, but we're going to plug in our points. And the reason I say that is because of how this looks right now. F of x equals x minus 1. All right, so to start, I'm going to plug in -3 minus 1. If I type that in my calculator, I'm going to get -4. -2 minus 1. I'll get an answer of -3. -1 minus 1, -2. 0 minus 1, -1. 1 minus 1, 2 minus 1, 3 minus 1. Again, I'm getting these based on the equation they gave me. Now, the reason why I wanted you to treat this as if we didn't know what was happening is because we are looking at quadratic functions, but specifically this graph right here, f of x equals x minus 1, this is actually not a quadratic. And the reason we put this in here is to remind you guys that we can't be in robot mode. We can't just assume that it's always going to be a quadratic function because we're discussing quadratics. So we're going to look at a couple of key features once we graph this function. So if I go -3, -4, and then -2, -3, again, I'm just plotting these points that I've created here. -1, -2, 0, -1, 1, 0, 2, 1, 3, 2. So these points are all the points from my table. I can connect this graph. Best practice would be using a straight edge. when I see that it creates a straight line, I can confirm that this is a linear function, which means that some of the items we have listed below aren't applicable. As in a vertex, we do not have a vertex for a linear function. The zeros still can be applied here. A zero is where it crosses the x-axis, which is this right here. The only place this crosses the x-axis is at 1, 0. Next is the domain. With all linear functions, our domain is all real numbers. Is the vertex a minimum or maximum? That's not applicable because we don't have a vertex. Axis of symmetry, again, no vertex, no axis of symmetry. And the range. So for linear functions, both domain and range are all real numbers, meaning there isn't a limitation on either direction, up and down, side to side, of what kind of values we can have. At some point, every value will be part of either the x or the y value in this equation. Again, we don't want to go in robot mode. We want to make sure we're looking at the problem for what it is. X minus 1, if it was quadratic, it would have a squared exponent up here, but it does not, so I cannot just assume that it is going to be quadratic. All right, moving on to a function that visually we can confirm this is quadratic. We can confirm that because this is called a parabola. And this is the shape of a graph for quadratic functions. All right, real quick before we fill in our key features, I'm going to go ahead and give you your next code word. It's going to be the word owl. Go ahead and write that down because that'll be a word you're going to want to have later. All right, so now we don't have an equation given to us, but we do have a picture that we can use to help find information that's important. So our vertex is going to be that turning point in a graph. This turning point is located at over 3, up 4. So my vertex, 3, 4. The zeros of this function, that would be where it crosses the x-axis. The x-axis is all the way down here. This graph, because it's going down, U-turn and back up, it's never going to cross the x-axis, so we don't have any zeros for this graph. And that is the thing with quadratic functions. You could have it to where it never touches the x-axis. The domain, again, when we're looking at quadratic functions, my left to right movement is not limited. So all real numbers. The vertex, if I am looking at the turning point, this is the lowest position on this graph, so this is considered a minimum. The axis of symmetry is going to be the point, the line for this graph where this could be folded and both sides are mirror imaged. This location is going to be an x equals equation, and then I have to figure out what x value is this line on. If I look, 1, 2, 3, x equals 3 creates this vertical line. One thing I want to point out is we can help find our axis of symmetry by the x value in the vertex. That is a connection you can make from here on out. The next thing is the range, and again, it's limiting how my up and down movement works. Because we do have a turning point in a quadratic function, there is a point where this graph will not ever reach up and down wise. Again, because it's a minimum, this is the lowest point, and everything above it will work. Right here, my range is going to be all values that are 4 and above. So y is greater than or equal to 4. The next connection I would like to show you is that this range has to do with my vertex. However, the sign is going to depend on whether I was looking at a minimum or a maximum for my vertex. But specifically the value you'll get for the range will come from the vertex. All right, let me give you a second to write that down, and then we will continue on with our notes. All right, hopefully by now you have written down the notes for this problem. And we are ready to move on to our third page of notes. So, looking at our next page, we have yet a few more graphs that we're going to look at. This time we are given an equation and we are given a graph to use to create ourselves, meaning I need to figure out what values plug in and work for this graph. Now, for the sake of building a table, yes, any x value would work because our domain is all real numbers, but it's going to need to be able to graph on here, so I wouldn't want to pick something really large because as I continue through bigger numbers, my graph is going to skyrocket. That's just the nature of how quadratic functions work. So for the sake of these notes, and if you're ever generating a table on your own, I would suggest using -3, -2, -1, 0, 1, 2, 3. Again, these are numbers I picked specifically, but I picked them because they're going to actually show up on this graph. If I go too far away from that from 0, 0, my graph might not show up on here, and then I don't have anything to plot. As far as finding my y values, I'm going to go ahead and plug this in and figure out what is going to give me my answer. Now, this is very important. If there is one thing to leave this lesson knowing, it is that the way you plug this into this equation matters. Specifically, there is a negative in front to start. It must start off my equation, but then I'm plugging in a -3 to square because that is the x value here. Notice I put it in parentheses. When you use your calculator, you're going to want to put this into parentheses or else it's going to cause you to have wrong answers. The next thing I'm going to do is -2 times in parentheses -3. This will assure that what you are doing will put the correct signs where they're supposed to go. This is how it needs to look when you type it into your calculator. Negative out front, parenthesis, -3, close parentheses, squared, -2, parenthesis, -3, parenthesis. When you hit enter, you should get the answer -3. Moving on, if I plugged in a -2, again, there's a negative out front that I must include. Then in parentheses, I'll put the -2 to square because this is just being plugged in for x, -2 times in parentheses -2. When I plug this into my calculator accurately, I should get 0 as an answer. Next, with -1, I put a negative, parenthesis, -1 squared, -2, parenthesis, -1. And again, if I'm moving too fast, you can always pause this video in the middle of me talking to catch yourself back up, to grab that calculator to figure out what's going on. That's the beauty of a video. You can pause, rewind, whatever you need to do. When you plug this in, you should get a value of 1. Moving forward, if I plug in a 0, I should get a value of 0. This is the first time we've had 2 points repeat, so this is the start of a mirror image. Then I plug in a 1. There is still a negative out front. For the sake of habit, I suggest putting the 1 in parentheses to avoid doing it wrong later on. And when I do this, I should get a value of -3, which then would support the mirroring action continuing because my next point matches what's happening above. Now I've run out of x values up here to match with, but it should be understood that if I had gone backwards to -4, it would match up, and backwards to -5, it would also match up. Okay, but again, I'm going to go ahead and continue to plug in my x value. Negative in parentheses 2 to the power of 2 minus 2 in parentheses times 2 is going to give me a value of -8. And then finally, I will plug in a 3. When I plug this in correctly, I should get a value of -15. I will now use these points to graph this parabola. So -3, -3, first point, then -2, 0, then negative 1, 1. Then I'm going to plot 0, 0. And again, that was the first place that I said, hey, look, here's a connection. And that's the first place where the two are sitting side across from each other. Next, my next point should be on this same line here. We'll see. 1, negative 3. I shouldn't just assume. I want to make sure I can confirm that these points match up. Yes, they should. But if something went wrong, that can be my way to check it. And next is 2, negative 8. Again, I don't have the negative 4 value over here, but we said if it had continued, that point would match up. And then finally, 3, negative 15. I can't put negative 15 on here. My graph stops at 10, but I can go ahead and connect these points for this parabola based on this information. Again, I made the conclusion to put this point here because I said it should match up if I had continued moving backwards to negative 4. So if you would like to include that on your graph as a point, negative 4, negative 8, where it matches up with my 2, negative 8, that supports why I made that point on my graph. All right. Next code word for you guys. Go ahead and fill this in. It is the word tree. Keep that in your notes. All right, so the vertex here. The vertex is going to be my turning point. Now, if we look at this compared to our original page, our previous page of notes, we looked at a graph that was facing upward. We are now looking at one that's facing downward, which means some of our answers below are going to be different. As for the vertex, it's still considered the turning point of my graph, which is going to be negative 1, 1. The zeros are going to be where I cross my x-axis. This is always what a 0 refers to. And on this graph, this is the first time we're seeing it cross twice, and that is 100% okay. And just to remind you, just because it crosses the x-axis twice does not mean that it is not a function, because our test for functions is a vertical line test. So my zeros are going to be negative 2, 0, and 0, 0. It is important to note these are where they cross the x-axis. I am not going to then go figure out, okay, where does it cross the y-axis and include it as well. The options for zeros, you could have no zeros, you could have 1 0, you could have 2 zeros. Please don't ever give 3 zeros as an answer, because that is not something that a quadratic function will have. Moving along our domain, again, there is no restriction moving left to right, so all real numbers. Now, this is the first place that we're going to see a change. The vertex now is the highest point on my graph. It turns around and continues back downward. So this is considered a maximum. Again, the axis of symmetry is going to play off of my vertex. And from the previous problem that we did, we said it's going to play off of the x value in my vertex. So x equals negative 1. It will always be a vertical line for a quadratic function. And finally, the range will come from the y value in my vertex. However, this time, I had said before, the sign that goes into this depends on a minimum or a maximum. Since this is the highest point, which is 1 as a y value, my y values are less than or equal to 1 because it's anything lower than or equal to 1. Okay? Pause the video if you need any extra time to fill anything out. If not, I'm going to keep moving along to the next situation where we are looking at only a table to find key features. When we are given only a table, we want to find some sort of pattern. Now, if you notice in previous problems, I've been connecting mirrored points, meaning the y values that repeat. If I look, x values 1 and 3 both have y values of 8. Then x values 0 and 4 both have y values of 5. And then x values of negative 1 and 5 both have y values of 0. If you look specifically in here, there's a point that is being built around. This right here is going to be our vertex, which is 2, 9. Okay, when you start to find points that mirror up, there should be a point left right in the middle that is kind of sandwiched inside Sometimes I might have to extend a graph to find that position, but this right here is going to be an indicator of a vertex when the points match up on either sides of it. Now for the zeros, I am looking for when my y value is 0, because that is when I'm going to cross the x-axis. So my zeros are going to be -1, 0, and 5, 0. Again, it could mean that we have to extend a table if we don't see two of them. We could only have one. The only way that would happen is if it showed up in my vertex. And if I had no x-intercepts, potentially extending a table might cause me to find that there was no 0 as a y value. And that's fine. That is 100% okay. The only thing we do not want to do is say that there are 3 zeros, because this right here is a y-intercept, not a 0. It is very common to lump this guy in 0, 5 into my zeros category here because you simply see a 0 in it, but 0 refers to x-intercepts, so this y-intercept is not a 0. All right, moving along, my domain. This is still going to be all real numbers. There are no restrictions. As for a minimum and a maximum, I want to look at my vertex and I want to decide, are the points when I move away from it getting bigger or smaller? That is what's going to help me decide, is this graph moving downwards or is it trending upwards? When I go and look at the points, my vertex being a 9, all of these y values are smaller than my vertex, which would mean that this graph is going to look something like this, where this point would be 2, 9. I've determined that because of what the numbers look like outside of my vertex. Because my graph looks like this, it's very similar to the previous problem, where this would be considered a maximum. Okay, the axis of symmetry, remember we said it plays on your vertex. It has to do with the x value because it is always a vertical line. So my axis of symmetry is x equals 2. Now for the range, I am again going to use my vertex to help me out. It's going to deal with the y value in my vertex. And again, because this is the highest point, my y values are going to be everything less than or equal to 9. Okay? All right, we have a couple more problems left on this last page of notes. The next one, we're looking at a table again. Remember some of the things I said in the previous problem about what happens when zeros, when no zeros, 1 0, 2 zeros are options, okay? Because it's going to come up in this guy right here. So first of all, for my vertex, given a table, I'm looking for where do my values start matching up, okay? Well, I see that they match up everywhere except for this one right here that's kind of smushed in the middle. Again, that's an indicator of a vertex. Now, this vertex has a y value of 0. This is something I'm looking for when I'm looking for the zeros of a function, but we had said in the previous problem, if the 0 shows up in my vertex, then there is only 1 0. This is the only time that you would only have 1 0, and it's when the vertex itself has the 0 as the y value, okay? Again, this right here is not a 0. This is a y-intercept, which is another key feature we want to keep in mind, not applicable for this answer right here. The domain is still all real numbers. As for a minimum and maximum, I'm going to go back to my vertex. I'm looking at the y values only, and I want to answer, are these y values bigger than my vertex or smaller? In this case, they're building up bigger, which means that vertex is the lowest point on my graph. Because it's the lowest point, it would be considered the minimum. Oh gosh, minimum. The axis of symmetry, which is always vertical, pulls from the x value in my vertex, x equals -3, and the range pulls from the y value. Because this is a minimum, it's every value that's going to be equal to or bigger than that, so y is greater than or equal to 0. All right, before we finish up for today and I give you some instructions on what to do with your code words, which, by the way, the last code word is going to be water. Let's answer a few questions that are kind of analyzing what we've done today. So the first thing says, how do you know, or how do you find the axis of symmetry if you were just looking at a table? Well, if I was just looking at a table, I've been referring to my vertex in connection with an axis of symmetry. So what I would look for is the x value of the vertex. Okay. Next, how do you find the range? Again, we used the y value in our vertex for range. So it's the y value of the vertex. Okay, so we can use that vertex to help us answer axis of symmetry and the range. And the final question is going to ask us, how do I know if a parabola has a minimum or a maximum? Well, each time we discuss the minimum or the maximum of a parabola, we said to go look at the vertex and see what kind of points were the y values surrounding that vertex. Okay, so we'd look at the vertex, we look at the y value, and we'd say, are the points surrounding the vertex bigger or smaller than this vertex point? So I'm looking for the numbers from the vertex. Numbers moving from vertex. If they are bigger than the vertex, that means that this graph has a minimum. Okay, and if these numbers are smaller than the vertex, the graph has a max. Okay, so these are very important key features to keep in mind when you are looking at quadratic functions. Understanding the basics of the attributes of a quadratic function is going to be absolutely essential. There will be questions asking for these key features throughout this unit. So you need to make sure that this is something that you are holding yourself accountable to become familiar with. Your homework for tonight is going to be 3 pages, I believe. From what I can see right now, it looks like 3 pages. I could be wrong. However, if you've stuck this out the entire time and you have all 4 words that I gave as code words throughout this lesson, what I want you to do, message me on Canvas. The 4 words, I'm sorry. Send me a message with the 4 code words I used during this lesson. If you do that, I will give you an automatic participation grade for your homework, and you will not have to worry about having it completed to be checked tomorrow. I will address this when I am back in the classroom. Send me a message. I'll send you back that I've gotten it, and you should be good to go. Now, the homework is a great way to practice what we have been talking, especially because tomorrow we're going to continue to progress what we've been talking about. There are some great multiple choice questions. There are some situations where they're looking at linear versus quadratic and being able to tell the difference. So there are some great practice problems. However, if you went through these notes with me, wrote them all down, followed my video, and you wrote down the words I asked you to, if you'll message them to me, you have completed your homework requirement for the day. I must get this message though before Thursday. Second period, once second period starts on Thursday, this will no longer be an option, okay? So please make sure that you take care of that if you've finished through the whole video. If not, you're not even here to listen to this. If you have any questions over the lesson, please message me on Canvas. I will have my phone on me today, so I am able to help answer any questions you may have. Any examples, any practice problems that you need, please reach out and I will help you with what you need help with. Thank you and have a great day.